We now continue our tour of the biologically relevant organic molecules by moving into the world of lipids. So lipids are compounds of biological origin, also known as natural products, that are non-polar, and as a result are soluble in organic solvents rather than water. Okay, so here's a sort of classification scheme for lipids. So we can broadly classify lipids into two categories. Complex lipids can be hydrolyzed into something smaller, and simple lipids cannot be hydrolyzed. So those complex lipids include triglycerides, waxes, phospholipids, and the simple lipids include steroids, prostaglandins, and terpenes. We will look at examples of all of these in turn. But fatty acids are one of the components that triglycerides, waxes, and phospholipids are hydrolyzed into. So I want to begin by just looking at fatty acids. So fatty acids are long-chain carboxylic acids. They have between 10 and 30 carbons. And as an example, what I have drawn here is the 16-carbon fatty acid called palmitic acid. So this is an example of a saturated fatty acid. And what makes a fatty acid saturated is that it has no double bonds. It is saturated in hydrogen atoms, has the greatest number of hydrogens that you can possibly have for that number of carbons and a carboxylic acid functional group. Unsaturated fatty acids, on the other hand, have double bonds, so they are not saturated in hydrogen. So every double bond reduces the number of hydrogens by 2. So monounsaturated fatty acids have one double bond, and polyunsaturated fatty acids have multiple double bonds. Once we introduce the concept of double bonds, we have to raise the issue of alkene stereochemistry, because as you know, you can have either cis or trans geometry at an alkene. And in all naturally occurring fatty acids, the stereochemistry at the double bond is actually cis. Okay, so drawn here is the structure of the 18-carbon monounsaturated fatty acid called oleic acid. And you may have heard of this concept, especially in the realm of nutrition, of trans fats. Well, trans fats are unnatural fats with trans double bonds, and I'll talk a little bit more later about how we get trans fats. But they are a problem because your body's digestive enzymes are not capable of breaking down trans fats. The enzymes are specific for the shape of the cis fatty acids. So as a result, trans fats will actually accumulate in your arteries and they can cause problems there. Okay, so back to the shape. The cis geometry results in unsaturated fatty acids being bent. And that's especially clear in these space-filling models. So steric acid is the 18-carbon saturated fatty acid. Oleic acid we've actually met. And oleic acid, as you can see, is significantly bent relative to steric acid, which can basically form a straight chain. So as a result of the bent geometry, unsaturated fats do not crystallize as well. They cannot pack together one on top of each other because those bent arms will flop in each other's faces. So as a result, unsaturated fatty acids are going to tend to be liquids at room temperature, think oils, whereas saturated fatty acids tend to be solids at room temperature, think beef fat. Okay, so steric acid, being a solid, has a melting point of 69 degrees. And once again, as you've probably figured out from cooking, if you heat animal fat to a high enough temperature, it will in fact liquefy, but then once it cools again, it can solidify. Whereas oleic acid, the unsaturated fat, has a melting point of 13 degrees, which of course is below room temperature. Okay, a couple more properties of fatty acids for you. Most naturally occurring fatty acids have an even number of carbons because they are biosynthesized from 2 carbon fragments. They're actually built up 2 carbons by 2 carbons, with those 2 carbons originating as molecules of acetyl-CoA. And then for the monounsaturated fatty acids, the most common place to find the double bond is actually between carbon 9 and carbon 10. So now moving on to polyunsaturated fatty acids. These, as I've said, have more than one double bond. And what you need to know about them is that the double bonds are actually generally not conjugated. And you may have also heard of the term omega-3 fatty acids. And those are simply fatty acids with a double bond, 3 carbons from the omega end of the molecule, whereas the omega end is the end that does not contain the carboxylic acid. Okay, so I have an example here of a 22 carbon polyunsaturated fatty acid with 6 double bonds in it. So this is called DHA, docosahexaenoic acid. And this is actually one of the lipids that's naturally found in breast milk that is added to infant formula. If you look at some of these infant formulas, they say with DHA and ARA. This is the DHA. ARA is arachidonic acid, which is a 20 carbon fatty acid that has 4 double bonds in it. So then the next thing that we need to talk about are partially hydrogenated fats. And again, if you have read labels of ingredients, you can see things like, partially hydrogenated this, that, or the other type of oil. So partially hydrogenated soybean oil is one that comes to mind. So what happens is some polyunsaturated fats are treated industrially with hydrogen gas and a nickel catalyst. And this removes some, but not all of the double bonds, thus the partially hydrogenated fats. So hydrogenation, of course, is the reaction by which an alkene is treated with hydrogen. You add the hydrogen to the 2 carbons of the alkene to, at least at that point, end up with a saturated system. If you were to hydrogenate it completely, you would simply make a saturated fat, and those are readily available from natural sources, so there's no need to do that industrially. But turning polyunsaturated fats into monounsaturated fats or less polyunsaturated fats, oligounsaturated fats if you like, is actually important because some of these molecules have the property that they are spreadable solids, such as margarine and shortening, and those are actually important for cooking and baking especially. So trans fats occur as an unwanted byproduct of this process because the nickel catalysts that are catalysts for the hydrogenation reaction actually catalyze the isomerization of double bonds also, and they can isomerize a double bond from the cis geometry to the more stable trans geometry. Okay, so when 3 fatty acids are put together with a molecule of glycerol, glycerol is a 3-carbon alcohol with an OH on each carbon, the result is a triglyceride. So that is, as you can see, a triester of glycerol. So triglycerides are used in the human body for long-term energy storage. And they are efficient molecules for energy storage because if you look at a fatty acid, most of the carbon atoms are in low oxidation states. They're -2, -3 in some cases. So more energy is actually released per carbon atom when these molecules are oxidized to carbon dioxide through metabolism than what is released from consuming the same amount of protein or carbohydrate. And that's because the oxidation state of the carbon in either proteins or carbohydrates is generally higher. So you get less of an energetic payoff when you oxidize more highly oxidized starting materials all the way up to carbon dioxide. So that's actually the reason why fat contains 9 calories per gram, whereas protein and carbohydrate only contain 4 calories per gram. The last thing I want to talk about in the context of fatty acids and triglycerides is actually soap. So the anions, the conjugate base of fatty acids, serve as soaps because they have a nonpolar tail and a polar head. When you have the conjugate base of a carboxylic acid, you have the carboxylate anion. It is charged, it is very polar. And as a result, they have the property of being able to dissolve both nonpolar stuff in their nonpolar tail, but still have some solubility in water as a result of their polar head. So that's why soap is so effective at rinsing grease, washing grease, off of your hands, because the greasy part dissolves in the nonpolar tail of the soap molecules, and of course the polar head renders everything water soluble, and then it ends up down the drain, and well, then it's somebody else's problem. So soaps have actually been around for a very long time. We now have many, many, many different kinds of soaps and different products that have different properties. But originally, soaps were synthesized by taking animal fat and heating them in the presence of wood ash. And that is just another way of saying that you are hydrolyzing triglycerides, because animal fat is made of triglycerides, under basic conditions which are present in wood ash. Okay, so that's our start of our journey through lipids. We talked about fatty acids and triglycerides. In the next lesson, we will move to a discussion of terpenes.